You can see we just made a fractal. Well, it's a visual fractal. It's self-similar. So this is 11:44, February 8th, 2013. We're making a short video about the scale invariance of financial markets. The fractals, basically. And these processes turn up everywhere in nature. Fractals you usually possess what's called self-similar across scales. That is, as one zooms in or zooms out, the image and geometry has a similar topology. Topology just meaning, I guess, shape in reference to time. Self-similarity may be exact. This normally only occurs in mathematically defined, fractions or constraints, basically structures that we don't really see in the physical world. And we can look at some examples of that, but overall, with stochastics and iterations and chaos theory, with feedback, there's several types of fractals. There's exact fractals, there's approximate self-similarity fractals, like you see with the Juliet set. So on YouTube, just put in the Juliet set, and you'll see how it's a far more common type for this self-similarity. That is, as you look across the scales, the pattern is recognizable and similar to other scales. You see the snowman that looks like a little Buddha, and as you zoom in through millions and millions of log scales, or factors, and you see the same pattern turning up. So that's the second type of fractal. The other one is, statistical self-similarity, which you find basically in, I guess, like Brownian motion. Example, 1 over f noise. The fractal dimension is constant as one zooms in. So you see the same pattern nested in itself. And that's the whole nature of financial markets, this self-similarity. So very quickly, here we have on the top, we have the Koch snowflake. I'm pronouncing that wrong. Kosh, Koch snowflake. Here we have basically the Sierpinski blanket, I think it's called, or maybe it's more indicative of a Cantor set. But obviously, right here, this is the Sierpinski triangle. So here's the Koch snowflake. Again, it's just the iteration of adding the same shape, which is across, up, down, across, and then adding that to the same segment, and as you zoom in, you get it. Here's the Sierpinski triangle. And in chaos theory, you get this through many different processes. You can play the chaos game where you make 3 corners and you randomly roll a dice. 1 and 3, say 1 and 3, or 2 and 4 and 5 and 6 could be corners A, B, or C. And when you randomly put the dot halfway between the last point, this pattern emerges. It's called the chaos game. Look it up. You make the Sierpinski triangle through cellular automata rule number 90. There's like 4 different ways that you make the Sierpinski triangle. So in chaos theory, it's a strange attractor. It's the most eloquent example of a fractal. And then we have the Cantor set. It's just taking a segment and dividing it in half at a certain ratio. You got to look at the Cantor set. So basically, we're listening to Thomas Schumacher, Every Little Piece. A really good bit of British electro. We were looking at a nice quote by Isaac Newton. It is the glory of geometry that from so few principles fetched from within, it is able to accomplish so much. So I thought that was really eloquent. So, yeah. And we're looking at scale invariance. So for example, here's the Koch snowflake. We got to find it so you can see it. Here we go. Look, see how it's zooming in? It's scale invariant. It's self-similar. It just goes on forever. And here is another principle with scale invariance. What's it called? It's the Wiener process. You'll see it right here. If my computer responds and lets me scroll up. Okay, saw that. So here's the document we're going to look at. It is tiny.cc/Facebook FE, all lowercase. And we'll minimize that. And now we're going to bring up the charts. So we're looking at Facebook. We're looking at a pattern that I call the fractal. It's a double top divergence. It's a fractal double top divergence, but it's a fractal divergence. So these are terms I made up. So a fractal divergence is RSI divergence in 3 or more time frames that corresponds to the same place. A double top divergence is just a double top in price with RSI dropping, so that's just the double top divergence. And what I call a fractal double top divergence is just when you look at the time n+1, the completion point of the RSI signal, when you drop down to the lower time frame, you find the same pattern. So look, here's a daily chart, Facebook. We're pretty much very close. We're bang on actually the longest term Fibonacci retracement, the 61.8 from the IPO high to the past all-time low. We're bang on the 61.8% like fib level, the golden ratio. And look at RSI. It drops from at time n. N is a variable for an arbitrary point in time. It's just my convention to talk about locations on the, on the x-axis. So 82.5 down to. I should have done these little subtractions first. 77.1. So it's down minus 5.3%. And I hold the supposition that when divergences are more than 5%, there's an edge. So look, we're going to look now at January 28th and see what happened next. So we'll drop down to the 1 hour chart. So we're going to see 5 times more candles. So you'll see, okay, so here on the right, here is the start of the signal. This is the n+1 of the daily chart. This is now n+1 from the daily chart, but now it's our new pattern. So here now we have a new 1 hour time n and n+1. And so what happens is that we have another double top, and RSI drops 82.5 down to 73.7. So it drops like what? 4.45. So it's not quite 5%. So this is the hourly chart. So now we're going to drill down here to the market close on the 28th of January and look at the 5-minute chart to see what happened next. So here is the 5-minute chart, and look, here is 1940. Here's like this little Doji is a reversal pattern. It's 2050. It's 10 minutes before cash close, and we have an exactly 10% RSI divergence. So that's a strong reversal pattern. We have, and then we'll scroll ahead. So you can see we come off. So that's the 5-minute chart. So we'll close that, and then I'll show you the hourly chart and the daily chart. So this is not random. This is a convergence of buyers getting weak at a key Fibonacci resistance level across multiple time frames, and it's highly suggestive of a price reversal. If people say you cannot pick market tops, well, they don't know about applying a fractal market analysis approach across multiple time frames and looking for multiple RSI divergences greater than 5% on points of price instability, basically at confluences of strong technical levels from multiple time frames. So for some reason the graphics card, the screen capture software is conflicting with the packages. So we can just look at this chart. So it's tiny.cc/Facebook FD, fractal divergence FD. So, there it is there. We drop 5.3% across 10 candles. The PD value is like 0.5. It's 3,900 minutes. Hourly chart, the 4 hours, 4 bars. So 4.5 delta RSI divided by 4. The PD value is greater than 1, so there's an edge there. And then 5-minute chart, it's 13 bars divided by, so minus 10% RSI divided by 13 bars. It's not quite a PD ratio of 1. PD stands for price acceleration. It's an indicator that developed. It comes from classical physics because RSI, the change of RSI is synonymous with market velocity. It reflects a drop of momentum. So we can translate that into the equation for acceleration, which is change of velocity divided by change in time. So the change of RSI divided by change of time is a reflection of the market's deceleration, acceleration from classical physics. It's simple. The delta time is just the number of bars between time n and n plus 1. So basically you're still contrasting the y-axis to the x-axis, because RSI value here on the vertical axis, it's a difference between two numbers, and then the change of the y-axis in the bottom is just delta time. It's simple. And then you can see we come off, and we come off. So we come off from basically 32 bucks down to 28 bucks. So looking for a fractal divergence, double top divergence at a market structure point is a high probability way to pick a market top. That's my supposition. And I'm just looking, I was trying to work out the fractional dimension of the signals, but I didn't really come up with what I needed to. I'm just picking at it. So Wolfram science. So that's it. So we'll stop the video. You can look at the document and see it for yourself. It's beautiful. Oh, another fractal. Let's make some feedback. No, it's not responding. The processor's not responding well. We're not getting nice iterations of positive feedback. That's it. By exact atomic time, it's 11:55, 27 seconds, UTC, February 8th, 2013. And on Kite Frog, on Twitter, I'm Kite Frog. There's lots of this stuff. And on YouTube, you know, my YouTube channel.